the value of distance is the same, but the impact is obviously different. So what you want to do is incorporate what's called a scale. So here we're going to use a squared scaling. In general, it will be called polynomial scaling. All right, so we're going to propose a fitness issue, a third fitness function. So fitness number 3 of proposed solution as input will equal to, now you could put in the absolute value or not, square is going to take care of it. I'm going to put it in because technically you could have the negatives and your power may be odd. You may have negative issues. So I'll throw it in, even though parentheses in this case will make a difference. Anyway, by the weight of proposed solution. Yeah, and now we're going to square it. Raised to the, I think we've mentioned before, we did that when we talked about constants versus variables, so it means raised to the power of. Raised to the power of. Okay, this is called a quadratic scaling. Quadratic means raised to the power of 2. And is a specific case of the more general polynomial scaling. Have any function, but also can be raised to any power. All right. So when the 50 is away from 97, that's going to be a big value. When 96 is away from 97, that's going to be a small value. And the point is that now you're going to be able to differentiate based on how close the value is to 97, not just how close you are versus the next person, the next proposed solution. All right, so that's the issue of scaling. I'm sorry, Shu I asked the following, line 16. Let me go back up. Sorry about that. Didn't see it. Line 16. Oh, where am I? I'm sorry. Oh no. Tell me. Oh, give me hold on a second. Okay, good. I thought I deleted something. All right, let me go back up to line 16. Oh, what do I mean by this version is not quite there yet? The point is that it doesn't satisfy, meaning that fitness number 2 does not satisfy all of our concerns, all of our practical concerns, satisfy all of our intuitive concerns. Practical concerns yet, as now will be explained. Sorry. Now, again, just to emphasize, and it's very important you realize this, okay, let me put it in here. Please realize that that despite our displeasure or our concerns, despite our concerns, that's better. Despite our concerns, fitness number 2 and number 1 are valid fitness functions. The definition of a fitness function is only that it can have a comparative sense, but not necessarily does it have to do best job. Unfortunately, that's not part of the definition of fitness, that it should be the most meaningful and best job. It's just that it has to have a proper comparative effect, that if you have 2 numbers, you understand the difference between the 2. Are valid fitness functions because they allow for a comparative nature between solutions, a comparative experience, for comparative. Give me a second. because they allow for a comparative process, no, experience, no, a comparative nature, I don't know, between evaluation, comparative evaluation, lack of a better word, between proposed solutions. They do not have to be necessarily meaningful within the problem context, nor must they yield the best result. While you want that, that's unfortunately not part of the requirement of being a fitness function. All right, Shuhua, does that help you? You asked. Okay, great. All right, so now, so some people suggest that do this quadratic scaling. Why? Because the closer you are, the better you are. Again, because of minimization. We're interested in minimum. The goal, the perfect solution has a zero fitness, right? So the closer you are to B, the result is better. The farther you are isn't just simply 50 isn't simply away from 50 isn't simply, okay, let me make that point. So 50 versus 51 isn't simply one away, but rather, let's calculate it, 97 minus 50 squared versus 97 minus 51 squared. Okay, and let's do those values. Is equal to, so 97 minus 50 squared is 2209 versus 97 minus 97 versus 51, so it'll be, right? So equals 2209 versus 2116. Okay, again, minimum is minimal. Again, smaller is better, i.e. minimization, because that's what we're looking for. All right, now 2209 is 2116 equals what's that? 8493. So that's a big difference. It's not just one away. Right, but 96 versus 95 is only one away or four away. So being much closer, it gives a bigger impact when you're closer. So that is how people deal with this distinction, and they claim that fitness number 3 is a more accurate type of fitness function. So people claim that number 3 is a more accurate fitness function than fitness number 2 and fitness number 1. Okay, the other approach that some people use is called the penalty and or reward functions. Which basically, okay, so the point is that the penalty of being, let's say, 50, it's that issue of 50 versus 51, 50 and 51 being very far away relatively from 97 versus, let's think, versus 96 being pretty close to 97. So that would be a separate add-on, it's a function that will adjust the fitness function. All right, so okay, this concept, these extra functions. I hope that was clear. Let's make sure that word is here. I have to point out that is auxiliary. They're auxiliary functions. They're not in place of. They're in addition to. They're add-ons. Yeah, I spoke correctly. All right, so let's talk about the history. So in numerical analysis, that's where they were introduced. These functions are a means for converting a constrained mathematical problem into a non-constrained problem. Okay, how? By using the underlying function as the main function, and then adding on a penalty function, penalty reward function, whichever penalty just means minus, reward means plus, however you want to do it. It can be written one way or the other. Penalty profit, or reward, let's call it reward. Penalty reward function that adjusts the value obtained by the main function with a factor of the distance that the proposed solution is from the constraints. In this manner, in other words, in this manner, okay, that's not bad. In this manner, for example, the fitness number one function, which may not be a very good choice for this function, could be the basis of a very good penalty function. Reason being, because the negative, or its penalty function, in the sense that if you are over the constraint, a negative value obtains, which can be thought of as a penalty. Depending, again, plus or minus may be a penalty or reward depending on your minimum or maximum, but normally people think negative as a penalty, right? -3 in football or whatever. I don't know, however they have it, say it. Generally, so I'm just saying heuristically, the actual details you want. A negative value obtains, which usually indicates a penalty. But if if the proposed solution were within, but short of the constraint, then a positive value would result. Okay. Some would further emphasize these penalty reward values by raising them to a power. So some people take a scale and throw it on top of a penalty function. Okay, so I don't know who should be bolded or not. We'll worry about that later. Actually, it wasn't bad what I had, but okay. All right, so penalty reward functions. You throw in a separate function. So you have one function that truly is an evaluation score or fitness function if you like, and then you have a separate function that you add in, which simultaneously throws in another value to measure how close you are to the solution or not, independent of what the value should be. Note, then you could penalize if you 98 because you went over 97, but 96 versus 97 could be rewarded, even though it's, both are only one away. Anyway, that's obviously we aren't going to spend much time, but that's what some people do in these cases. Oh, it does. Good. All right. Be consistent. I'll put this one here and continue there. All right, fine. Enough said for today. Well, if we do, hopefully we will have time to do more examples of fitness functions, and we'll be able to to give more concrete examples. But the knapsack, I think, gives you a good understanding of the development of the different types of fitness functions that are available. Okay. Hopefully now we're ready for the next comment, and then let me just move it up, and then I'll ask you if you have any questions about this. Feel free to ask, so let me do so. And then we'll start right now the selection crossover mutation. All right, anybody have any other questions about these fitness functions? If anyone has any specific question? Okay. Feel free to ask anyway, but I'll continue talking. So selection in the context of genetic algorithms means bringing two individual solutions together to have children, solutions. I don't know how else to say that. To have child solutions. Okay, so bring the two solutions together. Obviously, in some point, somebody's going to call that mating. Right? You want to mate these solutions, whatever that means. I'll have to go through it. But that's the action. But that's not the point. The selection is, in other words, i.e., choosing the parents. Or they could choose themselves, however you want to phrase it. But basically, choosing the parents. All right. Now, so in the literature, there are mainly 4 types of selection, which we will go through. There are others, but these are the main categories that we've done. All right, in no particular order, maybe I forget. Anyway, one is purely random. We'll talk about that. So it's a purely random approach. Okay, the second one is called greedy. In the literature, also has been known to be called elitist. Although when you read the web, there's a little caveat. When we get to it, I'll emphasize that point, in that there's a misleading association from 1975 of Dijon, exactly what exactly is elitist. But so please be, I'm going to be careful, but do understand, because I always get every semester someone saying, well, I read on a website that Dijon, they don't know it's Dijon usually, but it's a quote from Dijon, that Dijon's thesis said the following. So you got to be careful. He was a little bit, admittedly, he was a little bit loose as to what elitist is. Anyway, so if you call it greedy, I think it'll be more intuitive, like a greedy algorithm. Anyway, next, roulette wheel, which actually is more like lottery than it is roulette wheel, and we'll talk about that in a second. It's not exactly like the Vegas roulette wheel, but it's sort of like. Anyway, roulette wheel is the one that Goldberg uses and assumes so, or models it for the purposes of what's going to be called at the end of the semester, the schema theorem. Okay, so Goldberg uses this approach. And mathematically, we're not today, but hopefully we'll mathematically model it at the end of the semester. We'll mathematically model this approach, and mathematically models this for the schema theorem. Okay, good. So that's roulette. And then finally, now this one has intuitively is easy. It's hard because in the literature there's just so many variations, because every little step could have a variation to it. So that's what gets confusing, admittedly. All I would tell you, just for confidence right now, is that the K tournament. So you're familiar with K tournament because all types of, what they call the brackets or tennis matches. So you know what sports tournaments are, and that's what it's inspired by. It really is. The problem becomes the way the literature takes it. There's just too many variations, and it gets very confusing. So I will tell you, so you can have a little bit of confidence, that if a K tournament question is asked on an exam, I will be very specific as to what is the variable and what you could assume is fixed. All right, but so admittedly, when we have that discussion, it's slightly messy. So just be aware of that and understand that it's not you, it's me. Well, it's not me, it's everybody. Okay, it's the literature. All right, so just understand that. That's the K tournament. The others are pretty clear. So okay. Anyway, let's get through to the first one, purely random. purely random approach. Now, one thing I'm going to emphasize, well, let's do it starting today, but I will certainly emphasize when we start the template tomorrow, Goldberg's algorithmic template for genetic algorithms, as presented in his book, is that I be very careful about parameters, to give them very specific names so that we're consistent and we always refer to them and you know what is a variable and what's a constant. All right, so I'm going to constantly assume and give names to variables. Okay, so for example, we are going to set a parent pool to the current generation, and I'll explain what that means. So current generation means all, well, too much bolding here. I just want to bold the variables. So we have parent pool, and then we have current generation. Okay, so let's put in a comment. So parent pool aren't actually the parents. Parent pool is the group of people who potentially could be parents. So parent pool are a subset of individuals who potentially can be parents. When we say pool, we mean potential, not actual, who potentially can be parents. Now, in the case of random, everybody can. So this is a little bit redundant. I'm setting it up for the others, just to be, as I said, to be consistent. So here, parent pool equals current generation, and current generation is everybody currently. Current generation is the population, the current population that is comprised of all potential solutions or suggested solutions, or of all suggested solutions. Actually suggested by the algorithm, it's not a theoretical of all. All right, suggested solutions by the genetic algorithm. All right. And this is a little bit redundant. Well, it's in name only. Nothing happened. The pool is the current generation. We're just giving it variable names. Again, later we'll make a distinction, but not here. All right, now, so again, as I said, we're considering all members of the generation as being the parent pool for the next generation. All right, so one last comment. We consider all members of the current generation to be in the parent pool of the next generation. Okay, we're trying to create the next generation. Okay, fine. So that's our comments. Good. Everybody's eligible. So that's very important. In the others, it's not the case. Not necessarily. But in this one, it's everybody is potentially a parent. Okay. Now, here's the sad part, which is while seemingly most fair, that everybody has equal access, while seemingly most fair, the fact is that in practice it doesn't do as well. Now, so okay. Is here, it's not because of the fact that we say all members, it's the randomness. So let's say it that way. Random algorithms in general do not perform well on hard problems. Comment, 1 second. Well, here we are. Okay, Andrew asks, this is because at random we do right, well, correct, Andrew. Yes, that's exactly right. Yes. Which is what I'm alluding to in this, what I just wrote. That is correct. That's a good way to say it, and it'll be accurate. All right, now, so then it begs the question, of course, how does GA differ from random, and why does GA do better when it does, right? So that's a good question. If we're saying random algorithms in general do not perform well on hard problems, so that begs the question, so why do we think that GA does better than standard random algorithms? If random doesn't do that well and GA is random, so why do we think that it actually generally that it does well when it can, right? That's a good question. So okay, so and specifically then, how does it differ, right? So if so, how does it differ? If it does do better, how does it differ? How does GA differ from random algorithms? All right, so that's something we're going to, hopefully by the end of tomorrow, you'll answer. But the point is that you're right. If you do not use a special or specially designed selection operator, and you only use purely random, then as of now, it's not that much more different. That's exactly the point. So, but that's all we can claim now because we haven't done more operations. But you'll see by tomorrow. But anyway, if you do not employ a specialized selection operator for GA, right, then considering what we have now, a GA won't be so different than random. Okay, but hopefully by tomorrow we'll have enough differences that will convince you to explain why it's better. Anyway, that's the case. So basically, in a nutshell, what do? You randomly take two individuals, and we said it a second ago, although we haven't defined it yet. You do selection, and you'll do crossover and mutation, and you'll produce some children, either one or two children. We'll get to it at that point. But we're only doing the first operator selection, and if we have time, crossover and mutation. All right. So the point is that what does random do? So in summary, just to clarify, in summary, A, purely random, simply randomly picks, chooses, or selects, however you want to say, two individuals who are the parents for children in the next generation. Okay. Again, we haven't described how what happens next, but for the purposes of selection, purely random, that's the case. Okay, that's the first one. So now, presented, so we'll do greedy next, which is, okay, first of all, any questions on random, please text and ask. All right, so B is greedy, also sometimes called elitist. All right, so in this context, not every individual of the generation is in consideration to being parents for the next generation. Okay, so we need another variable, which is top performance and top performance percentage. All right, top performance. So that's a variable, and that's why I'm bolding it. But I want to explain back. The reason I'm explaining this is that it's usually a percentage. It's given. All right, so you choose the parent pool, right? You form. It's more than choosing because at this point it's somewhat well defined. You form the parent pool, which is the people who are potentially parents. You form the parent pool to be the top performers of the current generation. To be the top performers in terms of fitness of the current generation. Again, these variables which are lists. Okay? So now, but such that, I guess we should say such that, whose fitness is the top percentage of all the fitnesses of all individuals, right? Fitnesses are let's say in plural, whose fitnesses are the top performance percentage of, this is our variable,